Welcome to my presentation over CFD analysis on a turbine. So here we go. So something about the fundamentals of CFD, one of the most important things is making sure that you have the right geometry, that you draw the geometry and model the geometry as best as you can. And when you mesh it, that's the most important part, because whenever you simulate it, you want your results to be outstanding and accurate. So the finer the meshing, the finer the results. And the whole idea behind CFD is to constantly be in pursuit of good and reliable results. And it gets into the next point here. The importance of CFD is to reduce cost and to allow theoretical assortment of reliable data when designing. So that's to say that it saves money when you do a CFD, so that you won't have to spend a lot of money having to simulate different prototypes on different engines, different other kinds of machine design, machine component design, etc. So this is one of the beauties of CFD, is you can simulate it using softwares like ANSYS, and there are many other softwares out there these days, but that's the gist of it. And so in this presentation, I'll present a quick CFD analysis of a turbine to analyze mostly of the velocity and pressure as air flows, and see the effects of it. So in the methodologies concerning the geometry, the inlet was measured to be 0.8 meters in diameter. The nozzle diameter was set to 0.4 meters. The radius of the combustion chamber section was 1.955 meters. As far as the meshing goes, I really wanted the meshing to be as fine as possible, so that I can get nice results that can resemble the physical effects of air flowing into a turbine. So with that said, I set my face meshing to quadrilateral applied. The element size were 2 millimeters in size for turbine walls, and the bias factor was set to 20. Refinement was automated, as well as the emphasis on a good mesh was placed on the walls for good solutions. So, and we'll see that as we go along this presentation. So concerning the solution setup, I set my inlet temperature at 461 Kelvin. The inlet pressure for the air was to be 405.3 kPa. The outlet temperature was set to 1,123 Kelvin. Airflow was set to 4.288 kilograms per second, and I was really looking for pressure and velocity contours. I set the models as viscous K epsilon transient flow, which is basically unsteady flow. Pressure and velocity contours were produced from running 50 timestamps with 0.05 time step sizes. This really just allowed there to be more time, more intervals for there to be better results as the simulation process. As far as residual monitors, they were set to 0.001 in absolute criteria. And as far as the results, here we go. So very much in what you'll see if you do some research concerning turbines like jet engines, you'll see that the velocity or the pressure is usually high towards the inlet of the turbine. So the pressure is high towards the inlet and low towards the nozzle. Whereas as far as velocity, velocity is low towards the inlet and high towards the nozzle. So for jet engines, this makes sense because that's what produces thrust. That extreme thrust push of air is what gives the airplane that force to propel forward. So I was really happy with this simulation as it was consistent with what we see in the real physical world. And so that's really the essence of CFD. This can go into many areas. It can go into um, the analysis of F1 cars to the analysis of airplane wings, and it's not even limited to those things. So these are my citations, and thank you for watching.